Hey. Hey. Say again. I cannot hear anything. But you can hear me? Can you nod if you hear me? I can still not hear you.
Okay.
I can hear you.
What about now? You can hear me now?
I can hear you now. Yeah.
Okay. I don't know. Was maybe I was connected to AI in the office until not so far. I don't know. Maybe some remaining in the memory, but
Happens. How was your week so far?
uh, busy, but it's okay. I never complain about that. It's good to have a good job and feeling that you are making some, you are adding some value to the company. So it's okay. I feel like.
Hey, Federico.
Hello. Hi, how are you?
Hi, Federico.
I'm the first
And
one, really.
You're the
Yeah.
first one. It's pretty crazy. If it's going to be cozy, then we can make a session all about you.
Okay.
How was your week, Federico?
It was fine. Quite fine.
Okay, both of you are not very excited about your week. What one friend of mine told me, that you say fine if it's like pretty bad and you don't want a follow-up question. It's like, you say fine, but don't ask me more. It's really, I don't want to talk about it. It's not good. Let's just move on to business.
No,
And-
it's quite difficult to find someone or to say something good. It's just weird to find someone who says fine, okay. Generally, here we speak more like,
Hi.
well,
Hey, Ania. Hey, Rodrigo.
there we are. Something like that.
Sorry, Federico, I think I cut you off. So
Okay.
you said here we say, so
Yes, like here we are or something like that. I don't know the expression in English, but you don't say like something positive. You just
so it's like in French, like ça va, ça va. So like, how's it going? It goes okay. Hey Anidi, hey Nicolas.
Hi, how are you, Andy?
Yeah, I'm happy to see you. For today I relearned a couple of things. That was quite exciting. Yeah.
Oh, Andy, Natalia mentioned that she already got the results, the most recent grades for the course.
Yes.
She haven't me yet, but as soon as she does, I will go through the BI reporting and perform again the regression and see.
Yeah, so there's actually one interesting thing that you can do. You can regress first the first half of the semester so far. Sorry, the second half on the first half. This gives you somehow the residual effect of the beginning. And then, no, I tell you offline. There's like some techniques to make it a bit more causal. So the thing we talked about last week to get some effect. Hey, Edison.
Okay.
Hey, Andy. Hey, everyone.
So far, we're perfectly nine. So today, because I'm now on the forum and I see all your questions. So there's space on the shared handout. As we have 2 more minutes, just write your questions, your general questions there. And today we have 2 main topics, and I would like to make space also for things that that you have. Yeah, it is on the shared handout under from the Mudboard space for your questions. So share screen.
I do have a question, but not sure if it's related. No, it's not related to the training. Maybe something that we can talk after the training, in case you know something about. Do you know about incremental learning? How to perform incremental learning on MobileNet? version 1?
You
It's
would need to
something that
give me more specific. Like you can call a lot of things incremental.
I want to train a specific neural network with some images. But I
Mhm.
want that I don't want to, each time I add some new images to have to train with the entire data set, just incrementally,
Perfect. Yeah,
a piece at a
can,
time.
that I can answer on the fly.
Okay. Okay.
Yeah.
Okay.
There's like that is a research topic which is actually quite big in at MIT, online learning.
Okay.
Hey Matteo, hey Andres. I have not greeted you yet. We start in 1 minute.
Hi.
Yes, also for you, you can write questions on the shared handout because the Mudboard was pretty empty. If you have things you would like to talk about, you can put them there. And it's 35, so we can start. Today, we have two main topics, which are two neural network architectures. And these are called RNNs and CNNs. And this will be the end of supervised learning for you. So to situate us in the course, we have like seen 1/2, which built up from classification, regression. There we saw perceptron, we saw Pegasus. I pointed out to you that SGD is everything. We saw different loss functions. We did multi-class classification. We also saw kernels. And now we saw neural networks and we see neural network architectures. This was all for, we have features and we have labels. And after the midterm, we're going to leave this space towards unsupervised learning, which means I just give you some data and you give me some representation, which is better. So this is the capstone of what do we do if you have features and we want labels. I have a couple goals for you. And before next time, I'm giving you a review of all of the things. I'm also going to collect some feedback from you today. So these are our goals. I will show you, I will explain you what a recurrent neural network is. I will also ask you before how many people know. And we will talk about unrolling of this recurrent neural network. Then here, derive is probably a bit strong. We will also talk through what for one specific version of the recurrent neural network updates are. And we will have one coding exercise today, which is finally, I told you that a lot of things are much easier in frameworks, uses a framework. And you will also use a framework in the project. And then the second part will be around convolutional neural networks. And I'm going to talk to you about how you can think of the functions that you're using here. One thing before we start, whenever I talk about these fancy architectures, I will say LSTM, I will say RNN, I will say CNN, and it looks terribly complicated. The thing that I propose to you, hey Mariana, is to think it's still just a function which has some weights and gives us some loss. And we can do gradients in the same way as we could before. It's not different. It's just more complicated functions, but we can still take the gradients with respect to these weights. So whatever you see, just think it's more of the same. It's not different really from a regression. For these general comments, do you have questions or comments? Hey, Marta. Okay, then for me to know, how many of you know, so can give a definition of a recurrent neural network? Just raise your hands like this. Okay, these are two. And who can define or can say how to apply how you apply a convolution in a convolutional neural network? Also raise your hand. Okay, this sounds great. So for the 2.5 people that already know what a recurrent neural network is,
Andy,
yes.
yesterday was the deadline for the lecture, so everyone should have read about these topics.
Okay, this is then sketchy that people didn't raise their hands. Okay, then I'm apparently off by 1 week, but so still, then okay, this is, you moderate me how fast we should go. I can tell you more than I have. This is very good to know. Good. Then with that, do you see my, no, we have my shared screen here still. So you take it then from here and just tell me when things are slow or fast. Then I'm mostly not telling you something new here. Okay. So the others that didn't raise their hands for give a definition of recurrent neural networks, was that you were shy, or was that you still see holes given this? For example, Ania, you didn't raise your hand. Or was that just a weird question from my side?
I was a little shy.
You were shy. Okay, great. So we can then maybe start together. So Ania, you and I. In what area do you apply recurrent neural networks, and why do you think the professors in this course have shown RNNs? So what kind of data do we apply them to?
I don't know. I think in many areas.
Okay, here. Rodrigo, can you help?
What I saw was that in images processing, they use a lot of neural networks.
So this is the second thing that we are going to see today. Convolutional neural networks, you use this a lot. Recurrent neural networks are for sequence data. So this is why it says here various input length. So this is a sequence of.
What I remember is that the strength of this technique is that you don't need to know beforehand how long the history is that you need to look at.
Yes.
The neural network is going to decide for itself how long or how much back it's going to look at.
So here, how much back this. So there was also an assumption, which was called the Markov assumption that you saw, maybe. The image that we have is, we have some input. So sequence of something is usually words. The thing that I'm mostly telling you about is the foundations of when Google Translate became so good. It was like, okay, and at that point it was still rule-based, but then it became very good because it used the techniques that I will have on the next slide here in LSTM, long short-term memory. And that was the breakthrough. And Marta's point is correct in that you have an input which is indexed by this index. And formally, you're not constrained by a certain structure how much you can put in, because the thing looks loopy. You have some way in which you're referring to an internal cell back and back again. And one important assumption here is that there's a so-called memory cell. And this memory cell stores things from earlier times. And there's like Marta's point is there in some sense correct. In LSTM, we will see it more concretely. You can store things back in time, but structurally the biggest thing is these can be arbitrarily long. Typically, we will use an embedding of our input into a space that we can work with. So that is a vector. And we use this one-hot encoding. So we say for each word in our vocabulary, we're going to use one dimension. Why is it that we not do an embedding like 1, 2, 3, 4, 5? So tree goes to 1, house goes to 2. Why not such an embedding? Andres, do you have an idea?
No, we don't. I'm thinking about.
There was one thing we had earlier on, which was we had this discussion about binary versus multi-class classification about the stars. And we had like a thing, yeah, what should we map to numbers and what should we not map to numbers? Does someone remember this? This was like maybe 5 weeks ago. So the thing here is, if we're having this to cat, so cat is 3, house is 2, tree is 1. Then in whatever output we produce, cat will be closer to house than to tree. It's just by the magic of by the nature of that these are numbers. If you're giving everything the same dimension, then everything is at the same distance. So the goal is not to introduce ordinal structure. So an order on things. Okay, then at each time point, we have a so-called, how is this node called? Edison?
Sorry, can you repeat, please, Andy?
Yeah. How is this node HT called?
My connection is bad. I don't understand. Sorry, please repeat.
How is this HT node called?
Hidden layer vector.
So it's the hidden node, and it also has another name, which made it very confusing. In the
Hidden layer vector.
It's also called visible. So it's a hidden layer in the sense of usual neural networks that we had before, and it's the visible hidden state in the sense that it is the memory that can refer to earlier points, referring to Marta's point. And then what we have is there's again weight matrix, bias, and activation function. This is what we know. The feature that we have now, and this makes this actually efficient, is we don't have a dependence of W on T. it is that the transition from input and our memory to the new hidden state is the same. Okay, then yeah, and do tell me if I'm going too slow here. I was like, I'm not here to bore you, and if I'm going too fast, do also ask me questions. This is one which is conceptually difficult, but in the coding exercise, you will see you can produce code with relatively few lines, even if it's conceptually complicated. I'll just give you 10 seconds. Yeah. Marta, did you want to say something?
No.
Ah, sorry. Okay, you were like, okay. So then this is a super loose picture, the one here. But what we can make it more concrete, what this means. So we have this hidden state and input and hidden state together as here in this one. Together through an activation function give us the next hidden state. And we can then say either at the end, there's a prediction. This would be sequence classification. We would take a text and we would say, okay, this is illicit content on Facebook. This is hate speech. Or we could have at each point, what would be an abdication of at each point outputting something? Federico or Nicolas? Yeah.
Translate a text, maybe?
Perfect. Yeah. And there, so here, this would be for sequence classification. And here, typically, we would have a bit of an offset. So we would first input a couple of inputs and let the memory learn, and then start outputting things after some time. But it's actually, for me, it's still a miracle that this works. But it works reasonably well. So here, this is sequence classification as an example. And then this would be, for example, translation. So we have here updated state, and we have an output of a word. Now the question is, how can we learn this? So when you see such a network, what are your thoughts given last week or given what you saw in the course? What do we do?
We train it.
Or maybe Yaneli, did you want to say something? You just unmuted yourself.
Oh, in this case, maybe backpropagation. I don't know.
Yeah, perfect.
I need to learn. I don't know.
Yeah, so backpropagation is exactly what we would do. And what does that mean in general? So how do these terms look for backpropagation? What do you do?
We adjust the parameters W to minimize the loss function.
And what do we do for that? Like, then you had some fun or less fun with the calculations in our last recitation, and also in the course.
It's a lot derivated. I don't know.
Yeah, it's all of the
to all the parameters.
Exactly.
Yes.
And now there is this feature that our W doesn't depend on T. How do we take this into account?
You need to correct the error and try to estimate new parameter. I don't know English.
Yeah. No, this is great, Yanidi. So here the thing is, and you will see in the coding exercise, and you maybe saw in the course already, but I want to stress that again. In frameworks, you do need to worry about this. Frameworks do the backpropagation for you. But the fact that this arrow here is the same as this arrow comes up in that you do chain rule back to the point where W appears. This is your first update. Then you chain even further back, so do chain rule further back and add this to your gradient. It doesn't change really much if you have formally an equality constraint on your weights. We also already talked about exploding and vanishing gradients last week. Does someone remember what this was about?
If you
Talked
don't
about it.
control, sorry.
No, go ahead.
If you don't control it, you can have the problem that the gradient starts becoming bigger and bigger. So that would mean it explodes, because we always look for a local maximum or minimum, right? So you can go in the wrong direction, and vanish is the way, the opposite, because you're multiplying lots of derivations, and then very quickly it can shrink or explode.
Mm-hmm. And this is great. And there also the question about local optima is an interesting one. If we were on a machine that could do perfect calculations, so real numbers, arbitrarily large, arbitrarily small, then there would not be a problem with vanishing or exploding gradients. The numbers would just be very large, and you would have multiplications of very large and very small numbers. This doesn't have, so this is then not an issue so much of local versus global optimum, but it's really a question of rounding error. And the problem is, if you have like here, let's say you have a text which is 50 words, and you do a character level, R and N. How high will be T then? So 50 words, and you do for each character a node. Do you have an idea, Yanidi? So how many characters do we about have in 50 words in Spanish?
$250.
That would be, so 50,
Maybe, I don't know how
yeah,
many characters.
five characters
per word in average. I don't know.
Yeah. So we have 250. So we have a number multiplied with the number multiplied with the number 250 times in a matrix multiplication. And this can be extremely huge. And then vanishing and exploding gradients can be terrible, especially when we take into account that we each time need to multiply with an activation function. And this is the reason last time we had this table with like linear and sigmoid and tangent hyperbolicus and the ReLU, and I told you also. Say again, Edison?
No, it's about the ReLU is a last function of activation.
Is less fun? I didn't understand this last sentence. Is less?
No, it's not. Andy, you talk about the function activations, and I complete the last function is ReLU. No more.
Okay, some of the connection was still bad. Did someone else get that better? I'm not sure. Can someone help me? It's so I'm not acting stupid here. So maybe, okay, maybe I try to make the point and you can tell me whether this is like, I half covered what you said. So in ReLU, the nice thing is gradient in the left part is exactly 0. and gradient on the right-hand side is exactly 1. Both either produces exactly a 0 value or don't change the value. So we cannot get exploding gradients. And we already, sorry, okay. Thanks, Edison. And there is, ReLU is an idea, and a second idea is to do something like this. What would this mean for us? Such a connection.
You're skipping a hidden state.
I'm skipping a hidden state, so I allow to access a state directly the earlier. And this is what I picked up when you were saying the network decides for itself how far it's going to look back. This would be, such a connection would be directly looking back. In the network as we have it now, it needs all to be passed through the memory states. But actually there is a way to make this more formal. Skipping formal, and this is called this long short-term memory. And the idea is there, sometimes in machine learning you tell nice stories about where things come from, and that this comes from human cognition. Here you should have seen, so if this was due yesterday, which I'm very sorry about then this guy comes maybe late, you should have seen something like this. Can someone formulate a question so that I know where you are here? So either a question or start some explanation around how such a diagram could look like, or you can just tell me I don't have any clue what this thing could do.
That one is the diagram of an LSTM, or
Perfect.
Or could be the diagram for another neural network.
So this is a diagram for an LSTM.
Yeah, I mean, basically you have this input and output that act like filters. When you get the input from the previous hidden state, the XT node decides what you really want to take into account and what not. And then also when you have to produce the output, there's this other function there that decides what you actually deliver as an output. Some other things you decide to ignore.
Yes. So here, this is a diagram that a colleague produced for a paper. It's really nice, and it's in pixel free. And we see here where all the data flows. But I find it, so this just shows this in our old network was just F. There was no fancy stuff, but here, what Marta says, there's some value which gives us, should I forget or should I update? Here, I could be interest. And we are then saying, depending on last hidden state and input, the forget activation and the interest activation. And we also can get an output. What this thing allows us is, this is the point, the big picture point that I hope that you can take through the weeks since we introduced softmax, maybe take away. When we take softmax, then we had a differentiable version of it. Sorry. We take an argmax. We had a differentiable version of it, which was a softmax. now we have here an LSTM update. What is the LSTM update a differentiable version of? This I didn't see in the course. If you think about programming, what do these formulas maybe represent? It's an if then else. So if forget is 1, then take the value of CT minus 1, else take this ton H of whatever I did before. Formally, I would like to do this. So I would like to write if forget CT equal CT minus 1, else CT equal, and we can write, this could be Python code. But I cannot write it. Why can I not write this? That's a big point that I was saying you in the beginning. Don't view this as different than others. What is the problem of a neural network that contains an if-else part? Well, we don't know what the gradient is. If-else is super jumpy. We can not do it. So this is why we take this LSTM update. It allows us to replicate it in differentiable fashion, if then else. And if, that like also for other things that come in the future, I don't know where it's going, but a lot of things that one can write in normal programming languages, there's some continuous form of it, which then is LSTM. I have now a coding exercise for you, and there I send you off, and you can look at it. It's then, if you have already submitted this, not so far, but it's actually a fun application. The goal, and here on the shared handout, you can find the links to everything, so also to these slides. I'm just going to walk you through the code. We have data, which gives us a bunch of names. English names, Italian names, and Japanese names, all transcribed into our alphabet, so into the Latin alphabet. And the goal is to predict what is English, what is Italian, and what is Japanese. There's a code that is finished that I adapted from somewhere on the internet, which lets you read in these names and prepares. Then there's also a train routine, which does all the training for you, given your model. There's also a predict routine, which in the end allows you to write something like, let me take the solution. No, this should be the solution. So here, can you give me a last name, Matteo? Okay. Or Marta, can you give me a last name that you would like to predict?
last name from
Any name, any name.
qué sé yo, Pérez.
So that is, so the net thinks that this is most likely English and less likely Italian or Japanese after some training. And the goal that is here for you is, and this I should show you here, is in this RNN to first write what are the different layers. So you should already have seen PyTorch. Is this correct? Can you nod? You have seen this now. So you have implemented something in PyTorch.
Not me.
Not you. So then this is next week. Okay, then I can walk you through here. So the task for you is to do some research and with me together explore some early parts of a framework. Typically in a framework, things look like you're first writing a function which gives you an instance of the object, a so-called constructor, and you define here different layers. And here you are also asked to implement some other layers. So we could have here linear 1, and then you put something which is then called a layer. I will give to you a link. These are 3 lines, and the second thing are also 3 lines. I want to have you explore that together. The second one is then a function called forward. This is in this framework that we're using, PyTorch, which is backed by Facebook one, where you say you have combined is some output of a certain layer, which is here called torch.cat, that maps words to categorical variables. So that is going to give you a one-hot encoding. And then you can do something like x equal to self.linear1 of combined. Has someone of you worked with any deep learning framework, for example, for feed-forward neural networks? So anything in TensorFlow or anything in PyTorch? Maybe raise hand, or has looked at the tasks in the course already. Okay, so we have something new here. Nidhi, you're back. So here, here I'm going to give you, so I think I would like to send you off into breakout rooms to read the code together and formulate questions first. We can still then solve this one together, but I think it's here good that you inspect and look at what do the different things do, and ask some questions on the code. That will help you in the upcoming project, definitely. So for now, everyone, please download the code that is on the linked on the shared handout. And I'm going to give you now around 10 minutes to have a first look at the code. So all the files, and identify what is actually needed here. And then we're going to come back. And also use this shared handout to write more general questions that you have. Great. I'm going to open them. So far, all good. So today a bit more guided. I Okay, the breakout rooms are open and I'm going to jump around. You can ask all your questions. So for now, it's only reading code and formulating questions.
I can't see the option of breakout rooms.
Oh, now they're open, sorry. And again, shout when I should assign you. The others, do you
I'm looking for a group because I'm alone, so I'm waiting for
okay.
the others.
Perfect. I can just assign you.
Okay.
Gonzalo, do you know where you?
I don't remember why was my room. Sorry.
Okay, then I also put you into one.
Yes, thank you.
Gonzalo, do you remember where you were?
I think I am alone now. So
You're alone now, but you could form a group with Andres and
Yes,
other ones.
I'm number 2 generally.
So you can also go. You can all go to number 2 together.
Okay.
Welcome back. I checked with some of you who was not able to install PyTorch / run the code. Otherwise, we fix this now. Don't be shy. So we had it in one group that it didn't work. Okay, so then I will say one thing that I talked with one group about object orientation here. Can someone of you share what this line 5 does?
Define a new class.
Mm-hmm. And then, so here we had like, I think very nerdy conversation on what else happens here.
Yes, the class generates inherits all the parameters and the functions from nn.module that are in Torch in the second line.
And this comes from here. So there's a torch.nn for neural network. We import it as nn, and we say.
What I don't understand something, Andy. Generally, you inherit something that is from bigger. For example, you have a bigger class that is professor, and then you say MIT professor. No,
yes.
It's a special subclass.
Yes.
But in this case, you say it in the other way around. You say the superclass is the layer, and the subclass is the recurrent neural network.
So this great question. nn.module is not a layer. It is a module. So module here means it's the composition of different layers. So what we could for example say, a module could be an LSTM unit altogether, could be a collection of different nodes. But here it is mostly NN module requires that you define some layers, and it requires one function.
I have one question, sorry, Andy.
Sure.
Module is the complete neural network in this case.
RNN is the complete neural network. NN module, we can think of an abstract class, how you would implement any network.
Okay.
Yeah. So NN module requires two things: a constructor as every function, as every class, and a function forward. The function forward is the application of different functions that we want. So here it's like we take input and hidden, and we map it to combined using this category which does one-hot encoding. Then we take combined and we map it using the function that we define up here to a first hidden output. Then also from combined, we go to output. And then we do something a bit weird. We redefine output by its softmax. What you would often see is something like x is equal to self dot I to h of x. X is equal to self I to O of x. This is in an in a feed-forward neural network. You would see you take X, your input, you apply, you apply, you apply, you apply, you apply, and you don't even bother changing names. This is another a thing I talked about with another group, that actually the magic that happens in train is uncanny. This is the full backpropagation. So can someone of the group where we talked about these ones say something about these lines? Otherwise, you can also think about what could these lines be? Which tasks do we need to perform in a backpropagation in general?
You need to find a gradient and correct the parameters based on a learning rate and the grade minus the gradient.
Yeah. So the correcting the gradients happens in optimizer.step. Optimizer here we said is SGD. Step says take the learning rate of the optimizer and update the gradients. Loss.backward is a thing which is the output of criterion. So that is an object which comes also out of this framework, but it has a so loss will also be a so-called tensor, a generalized matrix, and it has a function backward. And this is what computes all of your gradients. It's amazing. We only need to know what is before. And now we have these lines. What do these lines do? Line tensor size, what could that be in text? So here I go back to drawing. So we're doing sequence classification. So this is all our words or all our characters. In our example here, it is all the characters in our name that we want to classify. And it says for each of these, take our line tensor I, which is our input word or input character, and our hidden node, and compute output and new hidden node. So this is our repeated application in our image that we saw for the recurrent neural network that we had. This is our forward pass. This computes the loss. This computes all gradients. And this is update all gradients. And here, we can then see how this is used in things, and I can answer Hugo's question. Here we then say, we loop through training points sometimes. We get a training point, and then we only say train to get something. And if you have new training data arising, we could just say in here, for data point in newly arrived data set, train off, and then here, what we have. So this is category tensor would be what are the different categories that we try to predict? Line tensor are our words. RNN is the instance of our module RNN. The optimizer is stochastic gradient descent, and our criterion is a loss function. This is all very this is all like conceptually abstract, but I hope so. I want to instill in you that things that are one line here, so especially in the train function, these 5 lines were complete projects for you before. This is immensely making your life easier when you know how to use the tool. And there's like this, which is PyTorch, which is big, and there's also TensorFlow, which I work more in TensorFlow, and in this last week I can show you there some stuff, or we can. There's like divided there. Yes.
Can we take one step backwards, because I don't know, but for me it's the first time I hear about PyTorch.
Yes.
What it does and how it works. And you mentioned things like frameworks. I don't really know what that means.
Yeah, okay.
So I'm just watching at code, and it's really hard to follow.
Okay, yeah. So
I have the same problem. It's very hard to follow.
Okay, that's good. So frameworks, with frameworks, I mean pieces of code that pre-package, so that give you some functions that make functionalities that you often have in machine learning one-liners.
And those are part of the module, of the PyTorch module, the frameworks, or
so Torch is the framework. PyTorch is the framework. So when we import here Torch and N, this gives us very many different layers for neural networks. Then Torch Autograd, for example, is automatic gradient. It computes gradients. The thing that I always told you is the important thing to do. This does something important, something automatic. Here we import variable. Yeah, go ahead, Marta.
Okay. Where do you recommend us to, get a tutorial or get more familiar with the tools and the functionality that this offers?
You should actually, and I was thinking you had the whole thing only for next week, but you should use PyTorch in the next project. And a thing that I recommend for these ones, so for example, let's do a Google together.
For getting started,
So yeah, I think here, so a good example is to look at example code. So here, PyTorch, they're very interested in getting academics, and academics are typically not the best coders involved. So they give a lot of examples. And actually what you see here is the example that I give you. I adapted it from a PyTorch from a PyTorch example because I wanted to walk you through and get you some exposure to code, and also teach you a bit how to read code. And here they then say, okay, how do you turn names into tensors? They have these functions which I put into the data.py file. And then, okay, we do some things which look similar to what we had before. And then the magic comes, where they then say here, before we can do automatic differentiation, we do this. The tutorials, yes, you can read. I think there is also a different style. For me, it has been
examples.
Yeah, so this is an example.
Yeah. What you mean it works better for you looking at
for me to look at code and try to understand the code and question the code and then ask people that I trust with the code. Because yeah, and then also implement something. But this example here comes from one thing that you can directly find. And then yeah, so these are the two things that I wanted to get for you. So out of this, two things in code, one thing in normal. First, main learning. Recurrent neural networks are something you use for sequences that is mostly text. When you think about an application with text, Google recurrent neural network, and it will give you something that you can work with. Second, there are these frameworks which make things easy, and they consist out of you define your neural network as some class. This was the part that we saw in the train function, sorry, that we saw in the model function. And here I gave you something to do, which here said we're taking two linear ones as layers. So the first component is the architecture defined in a class. And the second component is then backpropagation, which looks almost the same always. No matter what you do in your network, you can almost have, you almost see always optimize the zero grad. Then there are some lines which do your stuff. You say almost exactly this line to compute your loss, almost exactly this line to compute your gradient, and almost exactly this line to update your gradient. So RNNs for text, define neural nets in classes, and use some code which is almost always the same to actually do the training. I would like to move on to CNN, unless you would like me to walk you through this code more. Because CNN is probably you have seen more. I'm also happy to give you here more of an introduction now. So yeah, this is who is in favor of reviewing some CNNs and giving you some like theory exercises on CNN. Can you raise your hand if you're in favor of that? Okay, who's in favor of continuing with PyTorch a bit more? Raise your hand now. Okay, so for the ones that PyTorch was a bit less, I'm happy to stay on and walk you through like a bit more after. Otherwise, for all of these sklearn, NumPy, Pandas, PyTorch, and TensorFlow, the documentation is amazing. I would not look toward data science blogs or anything weird. The documentation is amazing. And if you're struggling with the documentation, then I'm right now babysitting the forum, so you can also ask their questions on the even on PyTorch documentation. I'm like this, I'm happy to read up. That's, yeah. There also learn something because I'm mostly TensorFlow user. Good. So where do you apply CNNs? Who has seen a CNN before? That should now be. You have no, okay. Then I had a totally wrong impression. Okay. A convolutional neural network is something that you use for images. And it has a very different logic. It is, it consists of two operations, and it has another story. So let's say we have here our cute Andy walking around. Then the question is, can we identify some features on this image? So one feature, for example, would be a line here. And actually, there are things in computer graphics, which allow you to recognize a line. And these are called filters. Has anyone like used filters to make images sharper, for example? I probably like on our smartphones, we all do. Like sometimes you use filters on, yeah, I'm not on Instagram, but there you can make images sharper. And what these do are looking at some small part of your image and then moving around contrast or heightening contrast. The idea of a convolutional neural network is that you are doing transformations which look like filters, so like a sepia filter or transformation, and you concatenate them to get to some output. Let's see let's see more concretely what that can mean. And the calculation, I show you some great, I like GIF from Wikipedia. So let's say we have an input, which is a matrix or a tensor of size, height, times width, times number of channels. A channel could be, for example,
Andy,
yes.
I have, sorry, I interrupted.
Perfect, thank you.
But I have the problem with the tensor concept.
Yeah, so
can you explain about more about that?
So we have a number, which is a scalar. We have a vector, which is a list of scalars. We have a matrix, which is a list of lists of scalars. And now, sometimes we have a list of lists of scalars. So like a 3-dimensional matrix. And a 3-dimensional matrix is then called a tensor. And sometimes you also have a 4-dimensional matrix or a 5-dimensional matrix. So that is then a list of lists of lists of lists of lists of scalars, which we also call tensor. And PyTorch, all the frameworks work in tensors because what people that coded these things have realized that all of the calculations for computing gradients and so on actually doesn't change if you have higher dimensional matrix products. It's still linear and you do the same. So this input, if we think about a tensor, we can almost think like it's this 3-dimensional thing here. And there it could be, we have for each pixel, one number for blue, one number for red, and one number for yellow. This is often the case when we do image recognition. If you don't have black and white images, when you were doing the MNIST classification, there was a bit easier because MNIST is a black and white or a grayscale thing. But normally you have like, we, for example, have a 3-channel image that we communicate over. And then what we're doing is for each point, we are looking at a neighborhood and multiplying each value with a value in a so-called filter to input in here. And there I show you a I show you something. So this small image here is called the filter or kernel. And you almost place it over your input. And you multiply the values in the kernel with the values in your input to get the numbers. Now it's going to start again soon. So we take the input, we match up 5 here with 7, and we're going to multiply and sum up all the numbers. So here I actually cannot stop this. But this is an operation which has been which is something that was used as handcrafted already before convolutional neural networks came. This is why here the image says sharpened. This is something how you used to make images sharper earlier on. That you would say, let me take a point and take some linear combination of neighboring values to get a new value for this point. And it's clear that you can make contrasts sharper with this by saying, well, I'm actually going to take the value here minus a number times the neighboring values. Then when this part was a bit blacker than the neighboring ones, it even gets stronger, the contrast. And so you take the kernel and you move around for each point and you compute a kernel. So you compute an output. This we can think of like the weight matrix part in a normal network. Then there is a second part, which you can think of the activation function almost, which is called max pooling. And this says we take a submatrix. So we take our big input and we make it into smaller rectangles. And the smaller rectangles, we just take the maximum value. And the idea behind this is to say, let's think that 1046 are activations for, did I see a cat? And then it should only report, well, in the upper left part, somewhere I saw a cat. These max layers are then called quasi-invariant because you can move things around. And coming back to the slide that I showed you, you concatenate these. Oh, for some reason. Yeah. So we start with the input, then this was the GIF. Then we do this pooling. Then we do another time the GIF, another time the pooling. And then we can say flatten the matrix. So take the matrix and write it all into one long vector. So if you have like a matrix here, you can all take the second row, write it next to the first row, and so on. And you can pass it into a normal and usual network. This is another architecture. So we saw RNN as one architecture, which works for sequences and which gives you then some function which you can differentiate and you can take a gradient. Here you have convolutional neural networks, which takes tensors and does certain operations with them. The operations are still differentiable, so we can still do our normal stochastic gradient descent optimization. The layers that I showed in the GIF are called discrete convolutions. Some of you might have heard of convolution in terms of like, if you're an electrical engineer, there sometimes convolutions come up when you work in Fourier space. Otherwise, you might sum up other things. And before I give you one thing to explore a bit more, this moving around and this GIF, I post there the link. I want to give you two more definitions. So when we have this kernel that moves around, then we call this the kernel width and kernel size, kernel height.
Excuse me, Andy, how do you choose the kernel?
Say that again, sorry.
How do you choose the kernel?
The kernel is actually a weight. So this is learned. So the size of the kernel, yes, that is part of, that is like how many nodes you choose in a network, but the entries in the kernel are weights. The entries in the max pooling are chosen, but the kernel are weights.
Okay, but how do you choose those weights?
Using stochastic gradient descent.
Of the entire picture.
So here the nice thing is that typically the kernel is much smaller than the picture, because you're saying I'm only going to locally make a change. There's also a second thing that you do to reduce the size of your picture. That goes into a similar direction. Sometimes you only look at every second pixel. In your image. So here, every th pixel. And this is called stride. So here you have your image, you have your kernel, you move it around, and each time you take this sum of multiplications and get an output. If you have a very large stride, what does that mean for the output? Is the output larger or smaller for a large stride?
Smaller.
Yeah. So it can be almost 1. So it can be 1 if your stride is exactly the size of your image.
I have one question, sorry.
Yes, yes, that's great.
Sorry, a lot question.
It's great, it's great, it's great. Yeah.
You need one kernel for each layer, or just one kernel for all neural network?
You need, so for each, typically you would say you have one kernel per layer. If you say you have the same kernel in each layer, then we are back into, then we're like using a convolutional neural network architecture inside of a recurrent neural network architecture. And this exists. You would, for example, use this for video, but it's not so standard. So it's like typically you would have a code which says conv2d in PyTorch. This is how the layer is called. So x equals conv2d of x, x equals conv2d of x, and then 2 different sizes. And images that you would see, for example, is you have an image with 200 pixels by 200 pixels. Then you take some kernel, it's down to 50. Then you have some kernel, it's down to 20. Then you have some kernel, which brings you, then you have a layer, a fully connected layer, and you predict. And choosing these architecture is totally random. It's like there people just show that they get a very good error. It's not very much answered how you choose these architectures, but you make some assumptions. But this goes exactly into the question of why do you actually choose all of these weird models? It is to limit the number of parameters that you have. You have many kernels for different layers, but they are typically small compared to the image size. I would like to send you one time into a 10-minute, another 10-minute breakout room to explore a bit this convolved feature. I'm putting in the chat the 2 GIFs that I showed you. This is number 1, and this is number 2. And I have 2 questions for you. One is trying to apply this. You take a central point, you take the sum of the multiplications of all points around it, and you enter it into a new one. This is question 1. And question 2 is, how large is the output given a certain kernel size and a certain stride? Rodrigo, can you repeat the task so that I can check whether I said this clearly?
We have to say what is the converted feature, the result of putting the kernel in that input.
Result means?
The new matrix, the output.
Okay, this is for question 1. Yeah, and for question 2?
I don't really know. I just reading the
Okay, then I didn't do a good job. Sorry. So the first one is asking for the output matrix. The second is just asking for the shape, so the size of the output matrix. And here it's getting a bit warm with these definitions. The main thing conceptually that I want to take away, we have today the last session on neural networks, so on supervised learning. And these are highly complicated models, but using frameworks, the only thing you need to understand is how do you apply them on data? Everything else about training, about getting gradients and so on, if you can control the frameworks, they will take care of that for you, as long as you have something differentiable. And that allows us to have so sophisticated models. I'm going to send you out one more time into the same breakout rooms. And
it must be the kernel like 100% inside the input or not?
No, you can. So the kernel here, the kernel is always centered around the point. So if you're at a boundary point, then it overlaps. And that's actually a great question, because typically you also have a padding of the matrix, because what do you do when it's outside? And there typically you pad with 0. So you say there's nothing outside. That's a great question. I also put this as an image on the Jamboards. And you could use these. I open the rooms now.
And stride is 5. What is the dimension?
Okay. Welcome back, everyone. We're going into the final round of this session. So in the final round of supervised learning. Now we're at the top. The output of this one is how big?
It's the same as the input matrix.
This is correct under the assumption that we are.
The output is the same to the kernel, no? The dimension of the output.
This is in general false because it's always dependent on how many places in your matrix can you move the kernel.
Yes.
It could be that here it's just like 5 and 3. And in the solution that I gave you a non-padded solution. Padding here would say, okay, so if we want to center our kernel around this point, then, well, it doesn't quite fit. But it could fit if we write some values here. And one group, which was extremely fast and very impressive in this task, actually realized that in the GIF that I sent you, they padded using repetition of values on the border. I was very impressed. So here, well done, this group. So it's either 3 by 3 if you only take the internal ones, or either 3 by 3 or 5 by 5. This is in the padded case. Then, so non-padded. This one we don't take. Has someone found something for number 2?
Yeah.
So here, so all of the solutions to this I wrote in the handout PDF. There you can find them. Here, just an argument how we can see it. So we have a length of 75, and we would like to see if we have a kernel. So apparently, I don't mention padding here, so there's no padding. So when I move it around and I stop at every 5th stride, how many places can I put the matrix into? And
8 places.
How many? Say again.
8.
So 8 times 5. So we have like 5 to the left, 5 to the right, which are blocked. So that's 65. And then we can put at each 5 places. So that should be 13. Let's here quickly see whether I do this one correct. Otherwise, no, I'm relatively confident that it's not 8. But here, yeah, there are formulas as for everything.
You start with the first rectangle, isn't it? So it's 1, 6, 11, 16, 21,
yes,
until 75.
Yes, exactly. And here it's like I say 5 to the right, 5 to the left are gone. That is 65, and then 65 you divide by 5. So that's our stride, so it's 13. And the second question is, we apply a max pooling layer to this 13 times 13 thing. What is the dimension of the output? here, what we're doing is we take cells that are, we take 2 by 2 the cells. So the image is like in the one that I sent you for max pooling. You take upper left corner, upper right corner, bottom left corner, bottom right corner to get your output. So here it should also be 2 by 2. But let's you see it. I wrote it down. I'm like here. Yeah, I have something else for you, so I can even tell you this while you do something. I would like to get some feedback from you, and I put a link to a form that I used in this version with students that I taught earlier. So it's an adapted form for students that do like software engineering in apprenticeship school. So this was like a thing that I taught earlier before going to grad school and all this crazy stuff. And the link is in the feedback, and I also is also now in the chat. If you could take the minutes and fill this out. For the wrap up for today, I showed you 2 different architectures, and I showed you in the general possibility to implement something in frameworks. Whenever you see something crazy, ask the question, can I take a gradient of that? And then look for PyTorch or TensorFlow, how to do it. You never in your life, hopefully, will by hand compute a gradient anymore, because this can just AutoGrad do for you. And it almost feels like now we're all adults, but it's like there's still some more. But like we suffered a bit through this with like Pegasus and SGD and Perceptron, and now we're at the stage where all of this is just a one-liner: optimizer equal SGD, optimizer equal Atom, and it just does everything for you. And next week, I'm going to walk you through the whole story so far for the midterm. And after this, we're going to start into mixtures and the M algorithm and other stuff more in the direction of supervised learning. And that's going to have a very different vibe from what we do. Yeah, please fill out this form. And I know like we had more or less good ones, and here especially things that I concretely can improve to make this most effective for you. Leave this in there. Yeah. Otherwise, I'm here for all your questions, and feel free to go when you're done with the feedback. I'm now going to look up. Bye, Matteo.
Bye now. Survey
Bye.
completed. Bye. See you next week.
See you next week or whenever it's good.
Thank you, Andy. Bye-bye.
Bye.
Bye, everyone.
Bye.
Bye. See you
Bye.
next week.
Bye. See you
Bye.
next week.
See you.
Bye, Nicholas. Have a good evening.
Good evening, Andy. Good evening, everyone.
Okay.
Yeah, I like this topic, but it was also very complicated. I was,
But I believe that they are already understanding that the beauty of the neural network is that you don't need to do it by foot. You can use, so you can do it just using this kind of library. So it's,
yeah, I hope they don't get frustrated with these because they're actually quite amazing.
I don't think that they are frustrating.
So
Maybe a bit tired, but definitely not
yeah,
frustrated.
so the thing that if you want in the office hours, so I think you can just together look, for example, at the PyTorch code a bit more. I think there it's like, so how do you define that? What is the documentation of this nn.linear, for example? So here. So for example, I should send you the solution. I will send you the solution. So here it's like nn.linear, for example, applies a linear transformation to the incoming data. Math y x at plus b. This is an example of a layer. So when people come, then you see, okay, this is a matrix of input size plus hidden size times hidden size. And here, this plus is, for example, determined as a concatenation of lists. So this is going to be no, sorry. This is going to be just the length of the vector that is brought together. But here, yeah, feel what do you think is best? I think this code is very good to learn with. Relatively easy and has like a nice outcome.
I can retake it during the office hours. So
yeah. Otherwise, if there is something that yeah, something else that, but I don't know, like I think this worked example might be already good. In the office hour, you can also collect any topics that students really would like me to review before the midterm.
Yes, I can assure you that more than one is interested in see how they can give some extra hint or any suggestion that could lead them to perform their exam in the best possible way, the more simple way. So
yeah, so I can say some things. I haven't written the exam, but I can say some things where the person that wrote the exam said like this could be important.
And in advance, and that would be some maybe introduce a bit at a time some topics that you consider that could be relevant for the exam.
But no, can you tell me when is the midterm? Maybe I'm just off by a week.
Yes, I can. Let me see if I have it here. For final exam is on May 18, and the midterm is on April 5. It's on Monday, April 5. So We do have some sometimes yet, but it's about one. No, it's about one week. No, it can be. It's 25, 2 weeks. No, 1
Yeah,
week.
so we will do the review next week.
Next week. Okay.
Okay. Perfect.
I will send you a note about the question. If you can, when you have some chance, can replace with some suggestions on how to proceed with this incremental training.
Yeah, so I can tell you now. So stochastic gradient descent is something that works. So if you're, for example, taking here, let me show you one thing that I'm working on right now. Sorry, I'm having this only on a compute cluster. If it doesn't work, then I just.
Because it may seem trivial, but it is not. It's very hardware demanding and time demanding.
Yeah. So the thing that I would propose, if you, for example, use PyTorch, then you have the eval mode and the train mode. Eval is you predict, train is you train. And what you can do, and I don't know your exact scenario, but if you have an eval, you can train and you store the weights. There's like the function in Torch would be called, you can get a dictionary of the state of the network. This gives you all weights. You can store this, and then you can load it. And this is storing and loading models. And what I would propose here in your deployment scenario is, so if you have one machine which only applies, then you can say this machine, as part of a process, loads the state dict that a training machine trains.
Okay.
So you get new data, you train on one, like, I don't know how you virtualize, like, so let's say you have one Docker image on your virtual server, or you have somewhere else, like you have just one computer where the data arises. This is only there for training. They train, and when they reach a certain number of data points, so they train, and you store their weight dictionary. Whenever new data arises, they load it, and they increment. They do another round of stochastic gradient descent.
Okay.
So the thing is, the nice thing about stochastic gradient descent is it's exactly the same to take the complete data set, or take first half of the data set and then the other half of the data set. Doesn't make any difference, because it's a local, it's like stochastic gradient descent by definition is something which is online. So which processes one data point after the other.
Okay.
So here the proposal that I would have for you is use one of the frameworks, either TensorFlow or PyTorch, both have these features, and then say you have one machine, which is your training machine, and one is your deploy machine. they share one directory they write to. Train machine trains when when new data arises, first train machine loads WaitDict. Then train machine trains using new data. Then train machine stores new WaitDict on the shared directory. And then you have like regularly deploy reads WaitDict. And uses it.
Okay.
So instead of training, you only store the weights. In that way, you don't need to store even your training data set. You can just throw it away when you did the training.
Okay, let me try it that way.
Yeah. So there, if you have questions, we have on Signal. So, but I think like don't do it by hand and don't do it using Power BI.
No.
Do it in Python. This is like much less painful.
No, I was using Python, but I was using the framework I was using is MobileNet. So I'm not sure if I can. Let me see if I can also use PyTorch for this, because it's again it seems a trivial issue, but it is so far is not.
It's not
because,
a trivial issue. This is going to bring down your compute. Like if you need to train each time, this is going to kill your.
I need to just to put you an example. I need to train for each class around 2,000 images. It could take weeks before it completes. So it's too heavy. Even using a GPU is something that will demand too much hardware.
Did you try Google Colab Pro?
I believe I tried once, but it
was
not. The problem was the disconnection. After a certain time, it disconnect me. But
yeah,
maybe
but
I was not using it that way.
Because it has the tensor processing unit, especially images are lightning fast.
Okay.
It's very fast.
I will give it a shot.
Yeah. Okay, great. I think I sent you already the materials.
Let me check. Here my email. It is mail. It's a bit slow today. Okay, on UTech. Here. Yes, you did. Okay, material for today. Yep, I have it.
Yeah, perfect. Then, yeah, as soon as things come up, and especially when students give you things that they would like to review,
I will let you know. I will not wait until the next class. I can tell you in advance.
Perfect, great.
By this Friday after
Yeah,
the class.
this is perfect, because then I can just adjust to what people wanted to hear. Okay.